So this was supposed to be a nightlight talk about Auger on the first day. Unfortunately, due to some flight issues, I couldn't give it. So you probably heard some of this already. So I hope you will not get too much bored, and I will try to skip what you already heard about. So very briefly, this again is Auger. I just want to remind you how it is made. We have this very large surface detector array, 3,000 square kilometers. Each of these are water Cherenkov stations, more than 1,600 water Cherenkov stations. And we have 4 sites overlooking the area, each of them including 6 fluorescence telescopes to measure the longitudinal deployment of the shower. We also have 2 engineering arrays, one for the underground muon detectors and one for radio antennas. They are both in this region, which is an in-field region in which we have 2 grids of stations, one at 750 meters and one at 433 meters mutual distance to go lower in energy in our measurements. Now, I want immediately to let you know that we almost completed our upgrade, which we call Auger Prime. The idea of the upgrade is not to enlarge the area, which is already very big, but it's really to exploit the richness of the extensive air showers with the idea of getting more insight into the mass composition. You will see from everything I will show that what we are missing really is more information about the mass composition. So what we did was to include here a scintillator on top of each of the stations, a radio antenna, and improve everywhere the electronics. We have new electronics with increased dynamic range and very high quality characteristics. What I called before engineering arrays are now becoming real detector areas. We have the underground muon detectors covering all the in-field area, almost now we are not yet finished with this. And the radio antennas are now going to be 1,600, so one per each station. Now, all the results I will show pertain to phase 1, which is we call phase 1 what we collected before upgrading the detector. We are now in a transition period of commissioning everything to reach full efficiency with Auger Prime, and we hope to start with the phase 2 at the end of the year. Of course, we already have events now to check. Okay, going to the main characteristic of Auger, as you all know, I think this is a hybrid detector, meaning that it has 2 different ways of measuring showers. So we can measure the energy through the integral of the energy deposited in the atmosphere, the longitudinal profile. Integrating it, we get the primary energy, correcting by the invisible energy brought around by muons and neutrinos. And we can correlate this energy, which is directly measured, with an estimator of the energy from the surface detector, which is, this is the lateral distribution, that is the density of particles in each stations as a function of the distance to the core. S1000 is our energy estimator. And so if you take into account hybrid events, meaning the events that are measured by both detectors, you can correlate the two and get a data-driven calibration, which is not relying on models or in simulations. The energy resolution of the fluorescence detector is 8%. The systematic uncertainty on the energy scale is 14%. Okay, so the main result on the energy spectrum is shown here. This is the combined energy spectrum that Auger collected with basically almost all the phase 1 data, not all, but almost all. It's the combination of 5 different energy spectra made with different samples of events, and multiplying it by the third power of the energy, you can see all the features that are now defined with very high significance. Besides this region, which is measured in Cherenkov, and the region around the ankle and the suppression that we all know, this very large exposure, more than 80,000 square kilometers per radian year, allowed us to find this new feature, which we call in step. It's around 10 to the 19 electron volts, and it's going to provide even more information on the source's characteristics. Let me also underline that this is a measure that is completely independent on any assumption on the mass. This is also very important. Now, the most difficult measurement that we are doing is, of course, that of the mass, which is indirect. We do not measure directly the mass of the primary, but we do measure the distribution of the maximum of the shower development in atmosphere, which we call X-max. And these are the first two moments of this distribution, the min X-max and this standard deviation. The most precise measurement that we have here comes from the fluorescence detector. It's shown here in blue. And it is unfortunate that we run out of statistics in this region, and that, of course, the fluorescence detector has only 15% duty cycle, so we don't have so much statistics. But most recently, we could exploit the surface detector characteristics, the temporal and lateral distributions of the signals. We feed them to a machine learning code, and we derived this very large measurements of the X-max, which goes up to the extreme energies. We also have a completely independent measurements from the radio. This is the measurement in red from the engineering array of the radio, of course. Now you see that our composition is not constant. It's getting lighter up to 10 to the 18.2, more or less, and then goes to heavier masses. And this is confirmed looking at this decrease of the second moment, which goes to purer compositions as long as the energy increases. Of course, to go from here to the mass of the primary, you need to rely on models. And so this is the main systematic uncertainty that we have in this case. Now, this is stuck. Okay. So from the point of view of the measurement with the surface detector plus the deep neural network, we see here how the mean X-max goes in, as a function of the energy, the elongation rate. And you immediately see that thanks to the use of the surface detector and its 100% duty cycle, not only we can see that we are in agreement with the fluorescence detector measurements, which is here in empty symbols, but it's also possible to find features in this elongation rate. And these features are extremely interesting because they are somehow correlated to the features that we have in the spectrum. This is a very important thing that we just derived. We are submitting this paper soon. Another ingredient to the interpretation of this data comes from the multi-messengers that we can measure, because Auger is sensitive also to photons and neutrinos. This is the last results that we have on the search for diffuse fluxes of photons and neutrinos. We don't have any candidate, unfortunately, but you see that, for example, for photons, we have the gray, red, blue, and green points, which span 4 decades of energy. And here, at the highest energy, we can constrain the models about injection of pure proton elements from the sources. Here, in this region, we close the gap between the low energy and the high energy. There were no data here in this region. For neutrinos, the same. It's shown here. We are mostly sensitive to 10 to the 8 to the region around 10 to the 18 electron volts. Now, putting together mass, spectrum, and multi-messenger results, we can try an astrophysical interpretation. We start with a basic scenario of two populations of extragalactic sources, identical, homogeneous, uniformly distributed. We define the injection and take into account only propagation. And what we find is that the best description of our data comes from a very hard spectrum of the high energy component with quite low rigidity cutoff, and a soft low energy component which is not able to constrain the rigidity cutoff, plus maybe possibly an additional component. And similar conclusions can be obtained also with more refined models which take into account also in-source interactions. Now, if you put together all this information from the spectrum, from the composition, the very low rigidity cutoff of the high energy component, and the absence of cosmogenic neutrinos and photons, you can have a quite clear indication, at least, for the fact that the suppression is probably mainly due to the exhaustion of the sources rather than to propagation effects. There was a lot of discussion about the fact that the spectrum of the high energy component that we found was too hard, which is not in agreement with the expectation for the Fermi acceleration. But we started with not really realistic starting point at the beginning. We can think of something more realistic, for example, the discreteness of the sources. And in this case, we can find that the extragalactic magnetic fields that are between the Earth and the nearby sources indeed can affect the observed spectrum and reduce the low rigidity particle flux. You can introduce a suppression factor to the flux, and here you see the suppression factor plotted as a function of the energy in units of critical energy, and you see that when you go below a critical energy value, you have a suppression. And you also see that the slope of the high energy component becomes softer when you have a higher critical rigidity. The magnetic horizon plays a role if the normalized intersource distance and the critical rigidity multiplied together are between these two values, and this can result in strong limits on the extragalactic magnetic field in the local supercluster. There will be a talk later today about this, so you will hear all the details in a more precise way. There is another ingredient that is missing, that is, of course, the anisotropy. We looked to the possible anisotropy excesses in our data, both in large scale, when the energy of the particles is too low to allow to point to sources, and at intermediate scales at higher energies. The best result that we got quite some years ago was the observation of a dipolar anisotropy, which you see very well here, that is now at a significance of almost 7 sigma above 8 to 10 to the 18 electron volts. And you see also from the phase plot that this dipole points more than 110 degrees away from the galactic center that fits here. And this allows us to conclude that at this energy, the origin of the ultra energy cosmic rays is indeed extragalactic. We also saw that the dipolar amplitude is increasing with energy. And for this, we have, of course, many different interpretations. Here I show one of them, which assumes, taking into account the complexity of the problem, because you have to consider the mass composition, the source distribution, the magnetic fields, it takes into account the possibility that the anisotropy can come from the large-scale structure that surrounds us. And if you assume this model, taking into account the attenuation from these structures, you can end up with a dipolar amplitude that is indeed increasing with energy, as you expect. As going up in energy, the horizon is shrinking, and in quite good agreement with what the model predicts. This is, by the way, not possible if the composition is only protons, because it needs to have a mixed composition. We also did something ourselves, assuming equally luminous sources from the two mass source distribution and different source densities. We took a model for the sources that describes better our data in spectrum and composition. And again, we see that the dipole amplitude is somehow reproduced. This is the quadrupole. At the ultra energy sky, we have different searches. One is, for example, an all sky search for overdensity, scanning in energy and in Toppet radius. What we found is a clear excess in the Centaurus region, which is now at 4 sigma significance. And in about 4 or 5 years from now, it will be possible to reach a 5 sigma in this measurement. We also continued the catalog-based search that we conducted since quite some time. We have here 4 different catalogs, and you see that the post-trial p-value is here, and the significance for the 4 is this one, and well, the best significance is given by the starburst galaxies catalog. We are at 3.8 sigma. All of them capture an overdensity in the Centaurus region. The starburst galaxy model also points to a milder excess here in the region of the South Pole. Again, we have another term that we can include in our astrophysical interpretation. So what we could do was, for example, to include the arrival directions into the energy spectrum and mass composition as we did before. We start again with some model of the sources, including magnetic field blurring and some signal fraction that we leave free in the combined fit. And what we see is that including the arrival directions, the test statistics is allowing us to distinguish different candidates sources. This was not possible using just the energy and the mass. The data were described by a model which provides a 20% anisotropic signal in a window of 20 degrees above 40 eV, with dominated by nitrogen injection spectrum. Now, one of the most recent searches that we did, it's almost going to go to the archive and to be hopefully published soon, is a search for excesses along the supergalactic plane. Without showing you those results, I will just show you something that was already seen at the last ICRC, because in this search, we could also look at the 2 spots of telescope array, here and here. This is because if we use also inclined events, we can extend our declination region in the northern hemisphere. You see, we reach up to 45 degrees in declination, and we cover a large part of the regions in which telescope array claims excesses. You can see in these 2 columns that the number of events that we expect is basically identical, even if we don't have the same exposure that they provide. And with data of comparable size, we cannot confirm these successes. You see that the significance is compatible with isotropy. So for the moment, at the level of the analysis at which we are, we cannot confirm the claim of telescope array that the declination dependence that they see in the energy spectrum is due to the presence of excesses in regions of the northern hemisphere. This part you already heard yesterday by Ruben. I just go fast on this. We tested the prediction of hadronics models in many different ways with both the X-max, the muon numbers, all sorts of different analyses which are published in these papers. We note that even in the X-max, the difference among the models is of the order 1/3 of the difference between the X-max of proton and iron. And we have the muon puzzle that you know very well. We saw it in many different independent measurements. This is, for example, the case for vertical events. This is a top hat study in which we rely on what we measure in the electromagnetic component in the longitudinal profile, and we try to find modifying the simulations if we are able to describe the lateral distribution. And in this case, we see that there is a large deficit of muons in the models. The same is found in using the underground muon detectors. So in this case, this is a direct measurement. And we also see it again independently in inclined events, which is an indirect measurement, but somehow more direct because we have showers in inclined direction where the electromagnetic component is basically all absorbed. So practically all muons. And again, the muon deficit is confirmed. On the contrary, as you saw already yesterday, in the post-LHC models describe well the fluctuations of the muon number. So the fluctuations of the energy partition in the first interaction up to quite high energy is very well described. And this brings us to think that the most likely scenario is the accumulation of small deviations along the generations of the shower in the atmosphere. We also tested the prediction of hadronic models in another way, in a global fit in which we took into account both the X-max and the signal at ground with templates of free mass compositions, different hadronic models, but we allowed to adjust not only the hadronic part of the signal, but also to shift the X-max. Of course, if you shift the X-max, for example, lower in the atmosphere, you reduce the number of muons, so they are correlated. And what we found is that the best description of data is obtained if we put, in models, an X-max deeper by 20 to 50 grams per square centimeter, and an hadronic signal increased by an amount that is of the order of 15 to 25%. Okay, so I would just point now to what we think we can do with Auger prime. Of course, it's impossible to go into details, but what I want you to tell is that with Auger prime, we plan to have many different kinds of multi-hybrid events because we have many different detectors in our surface array. And as such, we will be able to separate the shower components, for example, using the water Cherenkov station and the SSD. Here you see the merit factor to distinguish between proton and iron is increasing a lot if you use also the scintillator response. We can use radio for inclined events together with the water Cherenkov station when the scintillator is not sensitive because it's too thin. And you see that, for example, for the elongation rate features, we will be able to reach a 5 sigma rejection of the three breaks in 7 or 8 years from now. And here you see, for example, what happens to the flux of photons when you use the Auger prime and run for 10 more years. So you see that we will be able to go down in the upper limits of the photons in this way. And by studying the flux of neutrinos, we will be able to also constrain the observed proton fraction that we can see. Of course, we hope that with the new electron able to be more sensitive, especially to photons and neutrinos, because of course we want to see one at least. So this is one of the hopes for the future. To conclude, I can. Conclude by telling you that we have a policy about publishing our data. There is a portal in which you can find the 10% of our data. You can see it at this address. Here you see you can download the 10% done to allow not only for outreach or for education, but also, as we already had in a couple of of examples, also other colleagues to have ideas and to be able to check them on our public data before maybe coming to us and proposing to do some analysis. And we plan to continue with this public release very soon, reaching 30% of it.
Thank you for the nice overview. Questions? Yes, please.
Thank you for your nice talk. When you were talking about looking for the events from TA, so for very inclined, you've mentioned, you've separated vertical and inclined events in Auger. So how certain are you of your inclined events? I mean, you separate them, so there is a difference, obviously.
Well, in this analysis, of course, we use them all together. We are very certain because we have different reconstructions, both for the vertical and inclined events. In inclined events, we have new maps that we use to reconstruct. So there is a very specific reconstruction with very clean study of all the systematics that are, of course, different in the two cases. But then in this analysis, we, of course, use everything together.
Thank you.
More questions? Online? Actually, I have a few questions.
Yes.
You had a summary of the models with delta X max and delta sigma. Would you please come back to the slide? The delta everything from models. Yes, exactly. What does it mean, this delta? Like delta X max, these are variations between models, 30 grams.
This is what it was just to introduce that in the different models, we could have variations in the X max evaluation that reaches 30 grams per square centimeter, which is quite large.
I see. And second column, this delta proton iron, the difference.
That's the difference in X max between
just more or less universal for all the models. Okay. Second question. Would you please come to the muon puzzle, your second slide? I think that was new to me. You had this energy dependence of muons.
Yes, this is what.
No, the other one. You had arrow bars, proton and iron lines. Yes, this one. If I look at the second slide, I wouldn't really call it muon puzzle. I would call it some tension, moderate tension.
Yes.
You see, it's if you come back to the previous one, like this LDFs, here indeed we have huge difference, huge puzzle. But there, look like things improved.
These are different analyses. They are independent, so you should take the result of each of them, and all of them together point to a muon deficit in the models. And of course, depending on what you look at, you have. What is important is that we have this independent measurement, which we were discussing yesterday. We have the X max that is measured by the fluorescence detector. So it's not only an indirect measurement from the surface detector.
Sorry, last question. If you come back to your magnetic horizon effect, do I understand correctly? It's a similar model, similar to the one of Denis Ferrara and Mikhail Lunga. They used for the source, something like magnetic field. But just you have this magnetic field by the galaxy, not by the source.
Sorry, I was looking for
there was a paper some 10 years ago by Denis Ferrara and Mikhail Lunga that one gets this hard spectra in the source just by the magnetic field. My impression that you have a similar effect, but just by the extragalactic space. The mechanism is very similar.
It's very similar, yes. But in this case, we are not considering the in-source interactions as they do. They have only one component.
Exactly. But mechanism is the same. And in addition to this, I'm a bit surprised. You expect something like up to 100 nanogauss. Is it really allowed
Well, there are the
I don't
possibilities.
remember precisely, but I remember some OU talks by Andrei Neronov some dozen of years ago.
But
I think there are quite some upper limits on the
there are
EGMF.
limits, but this is referring only to the local supercluster. This is very, very nearby sources. It's not
see.
to
I-
the general
No, no, not general
exogalactic.
GM. Okay, thank you. Thank you for your talk.